We start off today with a lecture by Donald Argus from JPL, the title given here, Change in Water at Earth's Surface from GPS Elastic Displacements and Grace Gravity, California Drought and Rise of the Great Lakes. And our agenda, whoops, go back one. Our agenda is first starting with the Woollard Award. And the Woollard Award, just to let you know, is for outstanding contributions in geology through the application of the principles and techniques of geophysics and geodynamics. We'll start today with a citation by Richard Gordon and then follow with the Woollard Awardee talk by Donald Argus. Richard?
We are here today to honor the remarkable achievements of Donald Francis Argus, principal scientist at Jet Propulsion Labs in Pasadena, California. He is this year's recipient of the George P. Woollard Award, given for outstanding contributions to geology through the application of the principles and techniques of geophysics. Don came to Northwestern University in the 1980s for graduate study after finishing a bachelor's degree at MIT. At Northwestern, he eventually joined my global tectonics group. He exhibited a broad set of skills, which included a structural mapping project with Bob Speed, excellent quantitative and computational skills, and ability to work with messy geophysical and geological data, and a talent for seeing a pattern in data before others did. While a graduate student at Northwestern, Don simultaneously developed skills in both marine geophysics and the nascent field of space geodesy. On this slide, I show a figure and the title and abstract of Don's highly cited marine geophysics-based work on the plate kinematics of the Atlantic. This was an important part of Nouvelle 1, to which Don was a central and important contributor. So his widely used and copied figure of motion along the Africa-Eurasia boundary is shown in the lower left. I've seen it copied in various ways in at least a dozen other publications since Don published this, and this particular paper I believe has been cited 500 times already. While still a graduate student, Don blazed a pioneering path in the application of space geodesy to global tectonics. And in this particular example from a paper published in 1990, as far as I know, this is the first paper in which a relative angular plate velocity determined just from space geodetic data was published. In this case, it's looking at the motion of the Pacific plate relative to the North American plate. In the panel at the left, we see the sites, several of the key sites used in the analysis for the Pacific plate and part of the North America plate. On the right, we have a comparison between the relative plate angular velocity determined only from VLBI, only from space geodetic data, shown as a red dot, red circle, filled red circle, and then an elliptical confidence limit outlined by red. And it's compared with the one from Nouvelle 1A, which is shown as a blue square. And you can say they nearly lie on top of one another. And part of what's remarkable about this is the VLBI represents 1 to 3 decades of data and of motion, whereas Nouvelle 1A is averaged over 3 million years. And so this is an important part of the body of evidence that shows that plate motions on a decadal time scale are very, very similar to those averaged over a few million years. So between those very different time scales, it shows that plate motion is steady. This next slide shows more of the work Don did while still just a graduate student. He treated the Sierra Nevada and California Central Valley as a microplate and then used space geodetic data, mainly VLBI, to estimate for the first time the motion of the Sierra microplate relative to North America. This puts powerful constraints on the orientation and rate of deformation in the Basin and Range province. He found that the Sierras moved at about 13 millimeters a year relative to stable North America. He combined it with results that we obtained from Nouvelle and also from space geodesy for Pacific North America motion to look at the differences, or basically the budget, how Pacific North America motion is mainly partitioned between slip along the San Andreas system on the one hand and motion across the Basin and Range province on the other. After finishing his PhD in 1990, Don moved to the Jet Propulsion Lab, where he has been since and where his career has blossomed. On this slide, I show an example of some of that work. This is a joint work with Mike Heflin, and as far as I know, it's the first set of relative plate angular velocities determined only from GPS data. And Don and Mike Heflin compared the results to Nouvelle 1A, but also to the results that Don had previously obtained from VLBI data. And as you can see, they're all in excellent agreement with one another. And this is providing even more evidence for the steadiness of plate motion, which we take for granted nowadays. At JPL, Don's work has moved in some new directions. One of them is a highly productive collaboration with Richard Peltier and other colleagues using space geodesy to constrain ice age terminal deglaciation. They're looking at where the ice was, how thick it was, when it was there, the specifics of the specific history of the deglaciation. Other work he's done is to also use space geodesy to analyze the kinematics and tectonics of coastal California between the transverse ranges and Cape Mendocino. This is shown from a slide from a figure in a paper in the GSA Bulletin in which he put important bounds on the slip budget for the San Andreas fault system. Also, for the first time, provided useful estimates of the rates of convergence that are raising the California coast ranges, which were much smaller than just a few millimeters a year than many workers were proposing at the time that he did the work. Complementing that work on Central California, he's also worked on the kinematics, tectonics, and seismic hazards in Southern California and the greater Los Angeles area, once again applying various forms of space geodetic data plus his deep knowledge of plate kinematics and how to describe it. He's also used space geodesy for global scale, plate scale, and continental scale tectonics. Here's an illustration from a paper of his in 2010 in which he shows all the geodetic sites on North America and then color code them as either being on stable North America, tectonically stable but affected by post-glacial rebound, or within deforming regions that are part of the diffuse plate boundary in the western U.S. And last but not least, he's been applying space geodesy to test and improve regional geohydrological models. We'll be hearing more about this today in the talk that he's giving, so I won't spend any more time on that. To sum up, Donald Largus is the 2020 Woollard Awardee in recognition of his forefront contributions to global tectonics using both marine geophysics and space geodesy, as a key contributor to Nouvelle 1 and Morville, and the leader of the group that estimated the Geodville set of relative plate angular plate velocities from multiple types of space geodetic data. For his work on regional tectonics, including tectonics of the western U.S. and California. For his work on seismic hazards. For his extensive work on the history of deglaciation, and his work on regional hydrology, which he'll be talking about shortly. Congratulations, Donald.
Thank you, Richard. That was so kind and generous for you to make that. Thank you so much. I want to thank the people of GSA, all the scientists, for getting me this award. I started at MIT as an undergrad. I took Rocks 101 with Frank Spear, and then I had undergraduate research opportunities with John Slater and Clark Birchfield. Then I moved to Northwestern University. Northwestern was wonderful. There was a 3-to-1 faculty to student ratio, and that was really good for learning a lot of stuff. Among the professors there were Dawn Ajurdi and Bob Speed, and they also got me caught up on the math and the physics that I may have not have learned at MIT. Seth Stein was always there to teach me the street smart stuff, how to advance my science, how to make contact with other scientists. Seth helped me as almost a faculty advisor the 1 year that Richard went to England. And I want to thank Richard Gordon. He taught me how to do science. He taught me how to write, statistics. I think most of all, he taught me how to have fun doing all the science and to find new things to do science on. And then I want to thank JPL and NASA for giving me the opportunity to apply the NASA space missions to science. I also had to change my science quite a bit to sort of fit in their missions. So thank you so much. I am so honored to receive this award. That's all. Hey, good afternoon. I'm honored to be receiving the George P. Woollard Award. Thank you so much. A lot of my research is on distinguishing between tectonic deformation and water deformation. Over the past several years, we've developed the capability to infer changes in water at Earth's surface using GPS vertical displacements. The first part of the talk is on water change in California. The second part on water change in the Great Lakes area. And you shall see that the new technique is bringing real constraints to hydrology. The first half of the talk is on water changes in California sustained over periods of either drought or heavy precipitation. The study is published in JGR 2017. The method we use is like that of a bathroom scale. When you step on a scale, the spring is depressed. We know the strength of the spring, therefore we can deduce your weight. Solid earth is the same way. When we put water on the earth, presses the earth down, we know the strength of the earth, so we can infer the change in water. The response is elastic, that is, it's immediate, and when we take the water off, solid earth completely recovers. Solid Earth's elastic response to a load is nearly known. If you put a disk of water on Earth's surface that's 1 meter thick and 14 kilometers wide, the Earth will subside 2.7 millimeters at the center of the load. The elastic response is tight in space at just 25 kilometers from the center of the load. The displacement is just half a millimeter. The elastic deformation is not very sensitive to rheology for surface loads more than 50 kilometers across. The Gutenberg-Berlin A Earth structure gives about the same response as that of PREM, and we calculate solid Earth's elastic response for a gravitating spherical stratified Earth. We distinguish between solid Earth's elastic response at left and porous response at right. If you put a bucket of water on the Earth, in most places, Earth subsides due to the weight of the load, and when you take the water off, it comes back up. However, on top of aquifers, when you put water on, it goes into the aquifer and fills up the pores and the silts, sands, and gravels making up the aquifer. The aquifer expands, and then when you pump out water, groundwater, from the aquifer, it subsides. So in the Central Valley, we've been pumping for a long time, and we've got a lot of subsidence. We can readily distinguish between the porous response and the elastic response. Mostly, if you look at the GPS series, you get a maximum vertical height in April, not October if the response is porous. If you're pumping groundwater out, the aquifer subsides fast, and if you're changing the amount of groundwater you pump, you get episodic motions that you can see in the GPS. We follow a series of 9 steps to infer water change from GPS. First, we get the mean monthly displacements each month from January 2006 to the present. Second, we omit aquifer sites and sites affected by volcanic activity. 3, we remove the displacement generated by atmospheric mass change. 4, we remove the elastic displacements produced by known surface water changes in artificial reservoirs. 5, we constrain the water change in the Central Valley to a hydrology model because we cannot get it from GPS. 6, we remove post-glacial rebound. 7, we remove Cascadia interseismic strain accumulation using the model of Li Wang 2018. 8, we invert for changes in total water each month from January 2006 to the present. We estimate pixels that are 1/4 degree in lawn pixels. We apply a Laplacian constraint to limit changes between adjacent pixels. And we estimate uncertainty in water change using linear propagation of errors. There are about 1,600 GPS sites in the western US. We omit the gold squares. Those are aquifer sites in the San Joaquin and Sacramento Valley, in western Utah in the Great Basin, those near Phoenix, and a few other places. We also omit the red triangles, volcanic activity, that's Long Valley Caldera, Yellowstone, and the Cascadia Arc. We omit the open diamonds, those sites affected by a post-seismic transient following the 2010 Baja earthquake. We're left with 1,300 GPS sites, that's 80%, and we use those and invert to infer change in total water storage. These are the 4 mountain provinces in California that we're going to integrate water change over: the Sierra Nevada, the Southern Cascade Mountains, the Klamath Mountains, and the Coast Ranges. The blues and magenta show the seasonal water gain. So the Sierra Nevada gains water in the autumn, the Sierra Nevada snow accumulates in the autumn and winter, and in the Klamath Mountains it's mostly rain infiltrating the ground that increases total water in the autumn and winter. The mean seasonal gain in water from October to April is compared between a hydrology model at left and that inferred from GPS at right. The blue color gradations are gain of 0.5 meter. The pink, magenta are gain of nearly 1 meter. So in the western US, in the autumn and winter, you get a lot of rain, so the amount of rain increases the total water and snow. And then in the spring and summer, the snow melts and runs off. And in the summertime, you get evaporation and you get a decrease in water. So you can see in the model, there's about 1 meter of water gained in the Sierras, the Cascades, the Rocky Mountains. And we recover that well with the GPS, although the GPS is smeared out in space a little bit relative to the hydrology model. But if you integrate the water change over an entire province, such as the Sierra Nevada or the Cascade Mountains, then you get a total water change nearly equal to that in the hydrology model. Part 1 of the talk is on changes in water in California sustained over periods of drought or years of heavy precipitation. So if you look, years 2012, 2013, 2014, and 2015 were 4 years of harsh drought, once in every 1,000-year drought. The 2 years before that were heavy precip, as were the 2 years after heavy precip. A water year starts in October 1st of the preceding year and it ends September 30th of that year. That way we measure the water as it accumulates in the autumn and winter. Water change in the 4 California mountain provinces from 2006 to 2017. The left axis is water volume in cubic kilometers. The right axis is water thickness in meters. The green is GPS. The pink right above it is the composite hydrology model. The magenta at the top is water change in artificial reservoirs, and the brown at the bottom is water change inferred from GRACE. So from GPS, we're inferring a total of 110 cubic kilometers of water loss from October 2011 to October 2015. That's a lot more than the 20 cubic kilometers of water loss in the composite hydrology model. In the 2 years before the harsh drought, 2010, 2011, we had 30 cubic kilometers of water gain. In the 2 years after the harsh drought, we had 60 cubic kilometers of water gain inferred from GPS. The takeaway is that in California's mountains, more water in the ground is lost during periods of drought and gained during periods of heavy precipitation than in the hydrology models. At left is vertical displacement from October 2009 to October 2011. The Sierra Nevada subsided 5 to 10 millimeters in elastic response to the increased water load. At right is the increase in water inferred from inverting the GPS data. The Sierra Nevada gained 1/4 to 1/2 a meter of water during the 2 years of heavy precipitation. At left is vertical displacement from October 2011 to October 2015 measured by GPS. The Sierra Nevada rose 15 to 24 millimeters during the 4 years of harsh drought. At right is water loss in meters. The Klamath Mountains lost 1/2 a meter to 3/4 of a meter of water. The Sierra Nevada lost 1/2 meter to over 1 meter of water. We're taking this from October to October. There's no snow accumulation in the mountains in October, so this all must be water changed in the ground. At right is the same thing, water loss inferred from GPS during the 4 years of harsh drought. At left is water change in the composite hydrology model. You can see right away they're totally different. So we have a huge amount of water loss inferred from GPS, none in the composite hydrology model. Water change in the Sierra Nevada province. The green is GPS. The pink at top is the composite hydrology model. the Sierra Nevada lost a total of 45 cubic kilometers of water during the 4 years of harsh drought. We take groundwater to be the difference between the two curves. Change in water inferred from GPS minus change in water in the composite hydrology model. And the blue segments of the curve show that melting snow infiltrates into the ground during the spring, in particular in years of heavy precipitation, 2011, 2017. And the orange segments show water is parched from the ground in the summer, particularly in the years of drought. So the blue numerals and the orange numerals are the amount of water gained or lost in cubic kilometers. In hydrology models, nearly all rain and melting snow runs off to the ocean. Hardly any is stored in the ground. So our finding requires that the hydrology models be revised. The hydrology models must have a greater capacity of the ground to store water. At left is vertical displacement from October 2015 to October 2017, measured by GPS. The Sierra Nevada fell 10 to 15 millimeters in response to heavy precipitation. At right is the water increase. The Sierra Nevada gained water a half a meter to 3/4 of a meter in the 2 years of heavy precipitation. Part 1b, why has the Sierra Nevada risen at 1.5 millimeters per year over the past 15 years? Hammond et al. Suggests it is tectonic uplift that normal slip along the Sierra Nevada frontal fault is causing the rise. Amos et al. Suggests it is solid Earth's elastic response to groundwater loss in the Central Valley. A review of geological observations, river incision rates, thermodynamic model of Salibi, and paleoseismology data along the Sierra Nevada frontal fault require that the uplift of the Sierra Nevada be 1/10 to half a millimeter per year over the past 500,000 years or past 4.5 million years. So it's not, the main reason is not tectonic uplift. The half-space model of Amos et al. Overstates solid Earth's elastic response to Central Valley groundwater loss by a factor of 2.5. Half-space model is in orange. A 3D gravitating spherical model is in pink. The difference is 2.5. If we furthermore add a stratified Earth, that's in blue. So Earth must be taken to be a sphere, not a half space. The vertical displacement of 5 GPS sites along the western edge of the Sierra Nevada. The observed is the blue dots. That predicted by our realistic 3D model of groundwater loss is in green. If you take the difference, it's the red, that's the residual. So you still get a lot of uplift, about 20 to 24 millimeters from October 2011 to October 2015 during the 4 years of harsh drought. In summary, of the 24 millimeters of uplift that we observed with GPS, 17 millimeters is solid Earth's elastic response to water loss in the Sierra Nevada itself. Just 5 millimeters is due to the elastic response to Central Valley groundwater loss, and 2 millimeters or less is due to tectonic uplift. Conclusions: in California's mountains, more water in the ground is lost during the drought and gained during heavy precipitation than in the hydrology models. Not all water and snow runs off immediately. Rather, melting snow in the spring infiltrates the ground, and in the summer, water is parched from the ground, so that the hydrology models must have a greater capacity to store water. The rise of the Sierra Nevada is due mainly to water loss in the Sierra Nevada itself. The Great Lakes water levels have risen about 1 meter over the past 8 years. We next explore solid Earth's elastic response and changes in gravity. The Great Lakes drainage basin in brown consists of all the rivers flowing into the Great Lakes. Water flows from Lake Superior to Lake Huron and Lake Michigan, which are at the same water level, to Lake Erie, to Lake Ontario, to the St. Lawrence River. Lake Superior rose about 3/4 of a meter from October 2012 to October 2019. Lake Michigan and Lake Huron rose 1.5 meters. The water volume of the Great Lakes increased by 285 cubic kilometers from 2012 to 2019. That's equal to the amount of ice lost from Greenland each year, and enough to lower global sea level by nearly 1 millimeter. Gauging measurements of the water level of the Great Lakes, Lake Superior rose about 1/2 meter in 2013 and 2014. Lake Huron and Lake Michigan, which are at the same level, rose about 1.5 meters from October 2012 to October 2019. The water lake levels furthermore have a seasonal oscillation about half a meter peak to peak each year. Solid Earth's elastic response to the big increase of water is nearly known. We calculated using a gravitating spherical stratified Earth with the rheology. The blue gradations are subsidence at 5 millimeters. The magenta color gradation is a subsidence of 15 millimeters. And I've got contours at 5 millimeter subsidence. Then the yellow contour is 10, another yellow at 15, and another yellow contour at 20 millimeters. So the seafloor of Lake Huron fell 23 millimeters, that's the max. Lake Michigan fell 21 millimeters. Lake Superior fell 15 millimeters. And then the land adjacent to the Great Lakes fell between 3 and 14 millimeters. We find that correcting for the elastic displacement straightens out the GPS positions as a function of time. So all the green circles are GPS sites with a reduction in vertical dispersion, the root mean square of 25% or greater. The yellow circles are other GPS sites. Vertical displacement of 6 GPS sites along or near the coast of the Great Lakes. The blue is the observed by GPS. The green is solid Earth's elastic response to the increase in water loading. And if you take the blue minus the green, you get the residual, which is the red. And you can see that by taking out the Great Lakes loading, it straightens out the positions. The red curves are straighter than the blue. We're using the latest and greatest estimates of GPS position from JPL satellite orbits and clocks and NGL's point positioning of GPS sites. Vertical motion across troop profiles through the area. WW prime is through Wisconsin and Illinois. M to M prime is through the lower peninsula of Michigan and Indiana. So on these two plots, distance is on the horizontal axis, vertical motion is along the vertical axis. The gray circles are the GPS estimates uncorrected for Great Lakes loading. The red are corrected for Great Lakes loading. The blue curve is post-glacial rebound in the I6G VM5A model. So we have uplift nearer Canada, and then we have pore bulge collapse in Michigan and Indiana. The green is the prediction of the Lambeck model. And you can see that correcting for Great Lakes loading moves the GPS estimates into better agreement with the 6G post-glacial rebound model. The mean rate of vertical motion from 2006 to 2019 from GPS. Most of the eastern half of the US has zero vertical motion. That's the white color gradation between 1 millimeter per year of subsidence and 1 millimeter per year of uplift. And the light blues to deep blues are subsidence. The lower peninsula of Michigan is subsiding at 1 to 2 millimeters per year. Wisconsin and Minnesota are subsiding at 2 to 4 millimeters per year. Along the Gulf Coast, there's an 800 kilometer stretch of Texas and Louisiana that's falling at 2 to 5 millimeters per year. So I'm next going to show a series of slides removing one phenomenon at a time. We first remove solid Earth's porous response to groundwater withdrawal and oil pumping. That eliminates the subsidence belt along the Gulf Coast. We find removing post-glacial rebound eliminates most of the subsidence. About 75% of the eastern half of the US has nearly zero vertical motion. There's still subsidence of Wisconsin and Minnesota at 1 to 3 millimeters per year. When we remove solid Earth's elastic response to Great Lakes water increase, we find even less subsidence. About 85% of the eastern US has nearly vertical motion, except in the Minnesota and the Dakotas. There we believe we need more forebulge collapse in the post-glacial rebound model. That we have nearly vertical zero motion brings us confidence we can use GPS vertical displacements and their fluctuations to infer changes in water at Earth's surface, and that we can combine with the GRACE data. Change in surface water in the Great Lakes in blue over a 250 cubic kilometer area is compared to change in water in the entire Great Lakes drainage basin. That's 750 cubic kilometers. You can see that the GRACE records the change in Great Lakes surface water. The peaks and troughs in the GRACE data each year precede those in the Great Lakes by about 6 months. At top left is surface water change in the Great Lakes from April 2013 to April 2016, measured by gauging stations. Lake Superior rose 0.5 meter. Michigan and Huron rose 1 meter. At top right is that same Great Lakes surface water, smeared by a Gaussian distribution with full width 334 kilometers. That's what we would expect to see with GRACE. The two GRACE satellites are at an altitude of 400 kilometers, so they have limited spatial resolution. At bottom left is the mass change actually observed with GRACE. That's JPL's mass solution. Mass is determined in each 3 degree by 3 degree pixel or mass. The values are water change in meters. So if we subtract the top right from the bottom left, we get the residual. At bottom right, we get hardly zero. So we're confident that our method of smearing the observed Great Lakes surface water by a Gaussian of 334 kilometers gives us the right approximation. At top is change in total water in the land part of the Great Lakes drainage basin. We calculate this to be total water from GRACE minus change in Great Lakes water smeared by a Gaussian of 334 kilometers. We find the peak-to-peak oscillation in water in the land part of the drainage basin to be 110 cubic kilometers. Each year, water on land increases by an average of 0.2 of a meter in the autumn and winter as snow accumulates and when evaporation is low. Then in the spring and the summer, the water decreases by 0.2 of a meter as the snow melts and runs off and when evaporation is high. Water on land is maximum in March, 6 months before Great Lakes surface water is maximum in September. The seasonal water oscillation inferred from GRACE at top is 2 times as big as that in the composite hydrology model, the pink at bottom. Okay, bottom, we infer groundwater change, the violet curve, to be water change in the land part of the Great Lakes drainage basin minus the composite hydrology model. The peak-to-peak seasonal oscillation in groundwater is about 50 cubic kilometers, or about 1/10 of a meter. Groundwater remained constant from 2004 to 2012. It may have increased by about 50 cubic kilometers when Great Lakes surface water increased, though there's a big uncertainty in that. Conclusions. The Great Lakes area has fallen due to the rise of the Great Lakes. The northern part of the eastern U.S. is subsiding at 1 to 4 millimeters per year, primarily because of forebulge collapse and viscous response to unloading of the lower tide ice sheet, and secondarily because of elastic Great Lakes loading. Water in the Great Lakes is maximum in September, 6 months after water on land is maximum in March. And the inference is we must correct GPS estimates of vertical motion for Great Lakes loading to better constrain models of post-glacial rebound. The capability of using GPS to infer water change is a big deal because we know we can now integrate GRACE gravity and GPS displacements to more accurately estimate change in total water at Earth's surface. I am happy to take questions now, or my contact information is at the bottom left of the slide. Thank you all for listening.
Don, question. Donna, Gertie here.
Yes.
So do you anticipate the Great Lakes will continue to rise?
I don't know. There's a study by Drew Gronwald at Michigan, and he's looking at how evaporation and precipitation changes each year, and he believes both are increasing as time goes on. So that's where they go for the answer, maybe.
Okay, thank you. Any others?
This is Richard Gordon. I have a question for Don. So early in the talk, you were talking about the hydrology of the Central Valley in California, and you said you couldn't apply your method and you had to use the existing hydrologic models. I didn't follow. Why is it that you couldn't use your method in the Central Valley? What's the issue?
Solid Earth has a porous response instead of an elastic response. So when you put the water on, the solid Earth does not go down because of the weight of the load. Instead, the water fills up the pores in the aquifer and it expands. So when you put water in the aquifer, it expands. And then when you take water out, like we do pumping, it contracts and subsides. That's why we've had so much subsidence in the Central Valley. So we must distinguish between the porous response and the elastic response and get rid of all the GPS sites that have a porous response. And you can tell a difference by looking at the oscillation each year and when vertical height is maximum. For the elastic sites, vertical height is maximum at the end of the summer when there's little water, but they're maximum in April for the sites in the aquifer because all the waters just went in it. So that's a limitation of the method. So now we're trying to use the GPS and the GRACE together to get a better estimate of water change in the Central Valley. The idea is GRACE gives the water change over a broad area. We use GPS to get water change in all the mountains surrounding the Sacramento San Joaquin River Valley, and then you can infer what's in the Central Valley to be the difference. Any other questions?
We do have one question from the audience from System. And the question is there a plan to improve the GIA model? There's still a small misfit.
We're working on it a little bit. Mostly we have to convince the scientists that the model we have is significantly better than 2 or 3 other models. Because the differences between those 3 models are a lot bigger than this little iteration we're going to do. So I actually have a talk at 2:30 a.m. Today or tomorrow in Germany, and I pre-recorded it. And so that's what that's on. So we're working on it, but it's a pretty small thing. Perhaps a bigger outstanding thing is we're trying to match the horizontal motions in North America. And right now the 6G model fits medium well, but there's a paper by Corne Kramer at Nevada, and he suggests that the GPS sites very far from the ice sheets are moving toward the ice sheets faster than in 6G. So that's a bigger advance that we're working on. Who's that question from?
System.
Okay. Any other question?
I don't see more questions from the chat. Not for now.
If I may ask a quick question.
Yes, please.
Okay, hi. I'm Marlon. I'm a PhD student at University of Michigan. Really interesting talk. I was wondering if you could comment on just the relative rates of the post-seismic deformation, not post-seismic, but the post-glacial deformation following like the ice sheets. Is that rate still really substantial compared to like the rate you see of like the water loading? Is it still ongoing?
Yes, the present rate of forebulge collapse is actually bigger than what the Great Lakes caused. So, you know, we can look at the paper and it shows you exactly how much it is. But the subsidence created by post-glacial rebound was 1 to 3 millimeters per year. And then that created by elastic loading was 1 or 2, but it varies over the 20-year length of the GPS data. So the paper has it exactly. Thank you.
Any other questions?
Hey, thank you, Don. Thank you, Richard, for the introduction. We'd like to call to your attention some other awards from our Geophysics and Geodynamics division. We have an Alan B. Cox Student Research Award given to Brandon Chase, and his title is listed here. That's around $2,900. And we also give a second smaller research award, the GSA, Geophysics and Geodynamics Division Student Research Award. And that went to Jang Han Chong, topic listed here. And that was for about $750. Brandon, Jang, if you're here, congratulations for work well done. I don't have control of the slides. I'd like to advance one, please. Okay, and then starting last year at the 2019 Phoenix GSA meeting, we presented or evaluated the different student presentations and picked 2 students for outstanding work, and that's Emma Blackwell from Arizona State, and there's her title, and Sarah Ann Nolt Caraway from Northern Arizona. So it's Arizona took all the prizes in mapping crustal deformation. And we just started that in 2019. We are doing evaluation this year at the 2020 meeting. And this year we will also be innovating an award of $200 for each outstanding student presentation. I'm not advancing. Next one, please. These are the Geophysics and Geodynamics Division officers. I'm Donna Jurdy, and I'm the chair this year. I'm from Northwestern. The vice chair is Ting Chen, who took the questions for Don. The secretary treasurer is Ben Drenth, and the past chair is Carol Stein. We have 2 student representatives, Reese Elling and Christopher Marlowe. We have a management board with a counselor. I hope you can hear me. My computer just flashed up that my internet connection is unstable. Next, please. Next slide, please. So you have an opportunity to, whoops, I have to go back one. You have an opportunity to go back 2. Here we go. We have elections coming up this summer, and we're requesting nominations in the spring for 2-year terms for both vice chair and secretary treasurer, as well as student representatives. So we're looking for volunteers or suggestions of people who might like to do this. And about the Geophysics Division, the mission is to bring together scientists interested in geophysics and geodynamics. And 2020 is our 49th anniversary. And so next year will be our 50th anniversary as a division of the GSA. Some details about our division. You see the membership in 2020 is 581. And this is the breakdown. We have 98 GSA fellows, 239 students. We have no teachers in our division, and the rest of the members make up 244. Now, you'll note though, since 2016, we've lost over 100 members. So this is a concern. GSA membership has also declined. I'm not sure of the relative amounts. We fund our activities through membership dues. Students get their first division free and then pay $4 for their second and third. And professional members give $10 towards the division. Our cash on hand is about $1,450. And we have one endowed fund right now, the Alan V. Cox Student Research Grant. And I showed you the winner of that. It was just about $3,000. And then last year, the Geophysics and Geodynamics Division started another fund in our name. And we currently have a balance of $4,400, a 41% increase in just 1 year. If we continue this, anything is possible. Our primary expenses are to fund the awards and research grants, and also with the annual meeting, when we get together again to meet in person, we have some meeting expenses for booths and lunches. Dates to think about. The next meeting, I hope, will be in person in Portland, Oregon, and you'll need to get your field trip proposals in by December 1st, topical sessions and short courses by February 1st of next year, and the abstract deadline will be in August. Early registration will be September. Now, for Woollard Award and GSA Fellow nominations, those are due on February 1st. Our future plans of the division. We plan on sustaining the increased level of geophysics and geodynamics sessions at the meeting. This year, we're the primary sponsor of 7, and we hope to expand participation in the GSA Student Presentation Awards. More students, and we need more judges to help us with this, and also recognize the students with larger awards and to get them involved in GSA. We hope to improve the fundraising for this and continue our activities. Suggestions or questions? I'm not sure if you're able to make them through the software. Please enjoy the rest of the meeting, and we hope to see you in person in Portland next October. So if you have any questions, I'd be happy to hear them. Ting, any questions on the?
No, we don't have any question from the chat right now.
Okay.
So if you have questions, you can, yeah, you can type
okay,
through.
So then thank you very much for joining the meeting, and congratulations again to Don and to the student winners. Goodbye.